the flatness problem. Have you ever, in the deep quiet of the night, looked up at the stars and felt a question forming? Not a question about life on other worlds or the names of constellations, but a deeper, more fundamental whisper from the cosmos. A question about the very stage upon which the grand drama of existence is played out. That stage is space itself. And the question is one of the greatest, most profound mysteries in all of science: the flatness problem. It doesn't sound very magical, does it? Flatness. It brings to mind plains, or a still pond, or a tabletop. But I promise you, the story I'm about to tell you is the closest thing we have to a true creation myth, backed by the razor's edge of cosmology. It's a tale that suggests our universe was born not from chaos, but from a breathtaking, impossible precision. A precision so fine, it defies belief. It hints that everything we see, the galaxies, the stars, this very planet, you and I, are here because of a single, perfect note struck at the dawn of time. To understand this, we need to take a journey, not a journey through space, but a journey into the nature of reality. Imagine the fabric of the cosmos not as empty nothingness, but as a living, breathing entity, a vast, elastic canvas. This canvas can be curved. The presence of matter and energy, planets, stars, you, me, warps this canvas, creating the dips and curves we understand as gravity. Now, when we talk about the overall shape of this cosmic canvas, physicists describe three fundamental possibilities. The first is a universe with positive curvature. Think of the surface of a perfect sphere. If you and a friend started walking in perfectly straight lines on this giant cosmic balloon, eventually you'd meet. It's a finite, closed universe. A universe of reunion. The second is a universe with negative curvature. This is much stranger. Imagine the shape of a saddle, or a sprawling, infinite paisley pattern. On this surface, if you and your friend started walking, you would diverge, racing away from each other into an ever-expanding, hyperbolic infinity. It's an open universe, a universe of eternal separation. And then there is the third possibility, the razor's edge, the perfect balance between the two. A universe with zero curvature, a flat universe. Not flat like a piece of paper, but flat in its geometry. On a flat surface, parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. It is the perfect, golden mean. The universe of perfect Euclidean balance. Now, for nearly a century, since Einstein's revolution, cosmologists have been trying to measure the shape of our cosmic canvas. And with satellites like the WMAP and the Planck Observatory, we have our answer. They have mapped the faint, ancient glow of the Big Bang itself, the cosmic microwave background, the first light of creation, frozen in time and filling all of space. And the result? The data is unequivocal. Our universe is flat. Astonishingly, perfectly flat. And this is where the mystery begins. Because this flatness is not just a happy accident. It is a problem of cosmic proportions. You see, the universe is dynamic. It's expanding. It has been for 13.8 billion years. And as it expands, any initial curvature it had would have been magnified. Think of that cosmic canvas. If it started with even the tiniest positive curve, like the bud of a sphere, the expansion would have blown that bud up into a vast, closed cosmos. If it had the slightest negative curve, a whisper of a saddle shape, the expansion would have stretched it into a chaotic, hyperbolic nightmare. For our universe to be as flat as we measure it to be today, 13.8 billion years after the fact, it must have been flat at the beginning to an accuracy that is literally mind-boggling. How precise are we talking? Imagine a scale that measures the density of the entire cosmos. On one side, you have all the matter and energy that would cause it to collapse back on itself in a big crunch. On the other, all the energy that would cause it to fly apart into a thin, cold void. The flat universe is the perfect knife-edge balance between these two extremes. Now picture the most perfectly balanced scale you can imagine, perhaps the scales of Lady Justice herself. Now, in your mind, place a single grain of sand on one side. The imbalance would be catastrophic. The universe would either hurtle towards collapse or rip itself apart. But the precision required at the Big Bang was infinitely more delicate than that single grain of sand. It was more like balancing the entire known universe, every galaxy, every star, every planet, on a knife's edge, and then having to adjust that balance so perfectly that after 13.8 billion years of violent expansion, of galaxy formation, of stellar explosions, the scale has not tipped. It is still perfectly, impossibly level. The math tells us that at 1 second after the Big Bang, the density of the universe must have been tuned to 1 part in a million billion. That's a 1 followed by 15 zeros. But if we go back even further, to a fraction of a second after the beginning, the precision becomes almost mystical. It approaches 1 part in 10 to the power of 60. That's a 1 with 60 zeros after it. This isn't just balancing a grain of sand. This is balancing a single atom on the edge of a cosmic sword and having it remain there, unfaltering, for billions of years. This is the flatness problem. How could the universe have been born with such an impossibly specific, such an exquisitely fine-tuned initial condition? It seems like a miracle. It seems like divine intervention. It seems impossible. For decades, this problem haunted cosmology. It pointed to a flaw in our understanding. It was a cosmic whisper that we were missing a crucial chapter in the story of creation. And then, in the late 20th century, a radical, magnificent, and almost magical idea emerged from the minds of physicists like Alan Guth and others. An idea that doesn't just solve the flatness problem, but paints a picture of the newborn universe far grander and more spectacular than we had ever dreamed. They called it cosmic inflation. Imagine the moment of creation, not a bomb going off in a pre-existing space, but the sudden, violent emergence of space and time themselves. Now, the standard Big Bang theory pictures this as a steady, if rapid, expansion from that point onward. Inflation theory proposes something else. It says that in the first fleeting moment of existence, a fraction of a second so small we have no words for it, the universe underwent a growth spurt of such staggering, such unimaginable speed that it defies all analogy. Forget an explosion. Think of a piece of spacetime, smaller than a single proton, and then, in a time span so brief it makes a nanosecond look like an eternity, this tiny speck of reality inflated. It doubled in size, and then doubled again, and again, and again, in a runaway chain reaction. We're not talking about doubling a few times. We're talking about perhaps 100 doublings or more. In less than the blink of a cosmic eye, that subatomic speck was blown up to the size of a grapefruit, or larger. Now think about our canvas. Imagine you have a tiny, crumpled up piece of paper, a ball of foil. It's full of wild creases and curves. Now inflate it to the size of the Earth. What happens to its surface? The mountains and valleys become insignificant. The curvature smooths out. The local landscape becomes, for all intents and purposes, perfectly flat. This is the answer to the flatness problem. Our universe isn't flat because it was miraculously born that way. It's flat because it was stretched smooth in its infancy by this incredible, hyper-fast period of inflation. Any initial curvature, any wrinkles in the fabric of spacetime were ironed out by this phenomenal, exponential expansion. The universe was polished to a mirror finish on a scale so vast that our entire observable cosmos is just a tiny, flat patch on a surface whose true size and shape we cannot even comprehend. Inflation takes the miracle and turns it into physics. It provides a mechanism, a cosmic reset button that set the dials of the universe to their perfect, balanced values. But the implications are where the true magic lies. Inflation doesn't just explain flatness. It suggests that what we call our universe is just one bubble in a frothing, eternal, multiversal ocean. That the Big Bang was not a unique event, but a local phenomenon within a much grander meta-universe. That the fundamental constants of nature, the mass of an electron, the strength of gravity, might not be universal laws, but rather local bylaws, different in each of these infinite bubbling universes. We find ourselves in a flat universe, not because it's the only one, but because only in a universe with this precise balance could galaxies form, stars ignite, and life, consciousness, arise to ask the question in the first place. This idea, this majestic, humbling vision, transforms the flatness problem from a technical headache into a gateway to understanding our place in a reality of literally infinite possibilities. The perfect flatness of our cosmos is a fossil, a relic from a time before time, whispering to us of an epoch of impossible growth and hinting that we are but one dream in a sea of endless creation. The quest isn't over. The details of inflation are still being probed, and new mysteries await. But every time we look at the deep, flat silence of the cosmos, we are witnessing the echo of its most violent, most creative, and most defining moment. It is the universe's signature, written in geometry, telling us the story of its birth. If this journey into the heart of cosmology has sparked your imagination, if you feel that sense of wonder, then do me a favor. Like this video and subscribe to the channel. It truly helps us to keep exploring these profound mysteries together. And I'd love to hear your thoughts. What does this idea of a perfectly tuned, inflationary universe make you feel? Awe? Humility? Curiosity? Let me know in the comments below. The conversation is my favorite part. If you want to dive even deeper down this rabbit hole to explore the wild frontiers of the holographic principle, the multiverse, and the true nature of reality, I've written a book that I think you'll love. It's called Holographic Multiverse, and it's a guide to the most cutting-edge, mind-bending ideas in physics today. The link is in the description below if you'd like to check it out. Thank you for watching and for sharing this journey into the cosmic dawn. Remember to look up at the night sky and feel the flat, vast, and beautiful canvas upon which our story is written. Until next time.